Hello, everyone. Today I'm excited to talk to you about a fascinating and increasingly important topic, which is the extraction of gasoline from petroleum coke. Let's dive into it. First, let's establish some fundamental concepts. We all know gasoline. It's a volatile, flammable liquid that powers our combustion engines. But what about petroleum coke or petcoke as it's commonly known? Simply put, petcoke is a carbon-rich byproduct that comes from the oil refining process. More specifically, it's a carbonaceous solid formed during the thermal cracking of heavy oil fractions. You might find it in different forms like sponge coke, short coke, or needle coke. It's notable for its very high carbon content, typically ranging from 85 to 95%, although it can have variable amounts of sulfur and heavy metals. Now, now, you might be asking, what do we use petrol for currently? Well, it's quite versatile. It serves as a fuel in the cement and power industries. It's also a crucial anode material for aluminium production, and it can be used as a feedstock for gasification and in the creation of synthetic fuels. So, why are we focusing on extracting gasoline from this material? There are several compelling reasons. Firstly, it allows us to convert a low value residue petcoke into a valuable fuel. This process also contributes to reducing waste and emissions, which is vital for environmental sustainability. Furthermore, it enables refinery integration and enhances energy security. Ultimately, extracting gasoline from petcoke helps to bridge the supply-demand gap for fuel. Let's dive into the process overview, which involves four main stages. One, which is the gasification stage, the syngas cleanup, and three, fuel synthesis. Last but not the least, the refining, which leads to gasoline recovery. Let's break down each stage. With the stage one, which is the gasification. This is where we convert the petcoke into syngas, a crucial intermediate primarily composed of carbon monoxide and hydrogen. This conversion happens under very demanding conditions, high temperatures, typically between 1200 to 1600 degrees Celsius, and pressures ranging from 20 to 70 bar. There are different types of gasifiers used, including entrained flow, fluidicide bed, and fixed bed gasifiers. With the stage two, what is the syngas cleaning? Here, the syngas produced from gasification isn't perfectly clean. It contains impurities like hydrogen sulfide, particulate, and tars. So this this stage focuses on removing these unwanted components using various techniques such as filters, scrubbers, and acid gas removal systems. We also use this stage to adjust the ratio of hydrogen to carbon monoxide to ensure it's optimal for the subsequent fuel synthesis step. With the stage four, which is the fuel synthesis, here we have two primary routes for synthesizing fuel from the clean syngas. With the route A, which is the Fischer-Tropsch synthesis. In the Fischer-Tropsch process, carbon monoxide and hydrogen react to form hydrocarbons, typically using iron or cobalt as catalyst. This route generally produces longer chain molecules like paraffins and waxes to convert these into gasoline. Further processing, specifically hydrocracking, is required. With the route B, which is converting methanol to gasoline. Here, which we made it MTG for short. Here, the MTG route is a multi-step process. Syngas is first converted to methanol, which then transforms into dimethyl ether and finally into gasoline. This process commonly employs copper and zinc oxide and also ZSM5 catalyst. A significant advantage of the MTG route is that it can directly produce gasoline with a high octane rating, However, a key challenge to manage in this process is catalyst fouling. And with the stage 4, which is product recovery. Once the fuel is synthesized, the final stage is about recovering the gasoline and ensuring it meets quality specification. This involves processes like distillation, catalytic reforming, and blending. Our goal is to meet specific requirements. For example, achieving a research octane number greater than 91 and sulfur content less than 10 ppm. In addition to gasoline, this process also yields valuable byproducts such as diesel, LPG, and naphtha. Now let's take a look at the flowchart of the extraction process. Here, the diagram illustrates the flow from the delayed cooking unit, which feeds into a preheater. The preheater also receives input from two coker drums, indicating a cyclical or integrated process. From the preheater, the material moves to a fractionator. The fractionator separates the steam into different components. A vapor steam from the fractionator goes into a heat exchanger, and output from this heat exchanger is our desired gasoline. So separately, a resid or residue steam exits the fractionator and also passes through a heat exchanger, with its final output labeled delayed cooking, suggesting a recycling or further processing of the residue. Beyond the core chemical processes, effective plan layout and IT integration are crucial for the success of such an operation. The plant encompasses main process areas, control rooms, safety systems, and administrative zones. Information technology plays a vital role. Sensors provide real-time input and system delivers output through alarms and screens. Key software applications include the SCADA, which is the supervisory control and data acquisition, and HMI, which is also the human machine interface, and various modeling tools. For network connectivity, for network connectivity, we are looking at LAN, which is the local area network, using Ethernet with a star topology, and controller area network, which is the CAN bus for managing embedded systems within the plant. In conclusion, the integration of IT is paramount for enhancing both the efficiency and safety of these complex fuel processing operations. Automation enabled by this integration is absolutely vital. Looking to the future, digital technology will undoubtedly be crucial for the advancement and success of fuel processing industries. Thank you so much.